Okay, so let me explain what's going to happen today. I want to discuss some technical stuff regarding finding generators in different groups. And then we will switch to encryption decryption problem. And we will go through all the steps of the process and apply the encryption and decryption for several examples. Okay, I want to start with this Chinese reminder theorem number 2. So what does it say? It says that if you have ZMN star and the product of Zn star and Zn star, they are isomorphic in case n and m are coprime. And the rule here is exactly the same as it was given for the version without star. Let's write it simple like this. And the map in the opposite direction is given by exactly the same rule as it was for the version without star, because it's exactly the same map, but it provides a bijection for subsets. So the interesting part for this map is that this map also preserved multiplication. So this is an isomorphism of the groups where the operation is multiplication. And well, okay. And so yeah, so if you want to go in the opposite way, so it's done in the same way as for ZMN, ZM, Zn, because this guy is just a part of this set. This is just a subset here, and this map is exactly the same map as here, but it's just restricted to these two subsets. So if you want to find the opposite, the map in the opposite direction, you do what we did during the last seminar. Okay, and somehow this thing allows us to split every group of this form into a product of the groups of this form. So somehow we reduce the problem to the case where so if that was our n, so then we reduce the problem of computing this group on the left-hand side to the case of computing the same group, but for the case when n is a power of prime. And now I want to discuss the structure of this group, where P is prime, and we just okay. Let's start with some simple exercise. Let's discuss how to compute the generators of this group. Yeah, before doing that, so as I mentioned before, when P is odd, if P is odd prime, then this group is cyclic. This is a very important remark. So we know that we can find a generator here. And I want to discuss how to find a generator for this kind of groups. For example, it will be very important to know how to find a generator for a group like this, because we will use such groups for encryption decryption process. So how to find the generator here? Well, in general, well, you should use some brute force approach, where you just randomly pick elements and somehow check if an element is a generator or not. So a general approach is to pick a random element A from ZP star and check if it's a generator or not. And if it's not, you just pick it again until you find an element which is a generator. So we want to discuss a general procedure how to check if an element here is a generator. So I want to address this question here. So before doing that, let's try some brute force approach where we just go through all the elements and just recall how to find all the generators of this group. So just again, so the elements here are just 1, 2, 3, and 4. Can you compute the generators?
1.
No. 1 is not
2.
a generator because here the operation is multiplication, and 1 times 1 is 1. It's a neutral element.
It should be 2.
Okay, are there any other generators?
Maybe 3.
Okay, how to check this in a straightforward manner? Just you see, Z5 star contains 4 elements. So as a group, it must be isomorphic to Z4. So if an element is a generator, so the order of the element must be the order of the group. So the order of a generator must be 4. So we must compute the order for each element, and if the order is 4, then it's a generator. So the order of 1 is 1. So how to compute the order of 2? You just multiply. The first power is 2. The second power is 4, which is not 1. Let's find the next power. So that this is the second power. So the third power. You just multiply 4 by 2. You will get 8, and modulo 5, you will get 3. So it's not 1. And if you raise it to the fourth power, you will get automatically 1 because of the Lagrange theorem, or one of the corollaries of the Lagrange theorem. If you raise every element to the size of the group, you will get the neutral element. So the order of the element 2 is 4, because 4 is the least possible integer, giving you the neutral element when you rise to this power. So here the order is 4. If you repeat the same computation with the element 3, you see, if you multiply 3 by 3, you will get what? 9. And modular 5, let's say, you take 3 times 3, so the second power of the element 3, you will get 9. And modular 5, it's 4, so it's not 1. Then you compute the third power. It's 4 times 3. It's 12. It's 2 modular 5. So it's not 1. So it's the third power. And if you rise it again, you will get 1 because the fourth power is always 1. So 3 also has order 4. And if you multiply 4 by 4, you will get 16, and 16 modular 5 is already 1, so the order of 4 is 2. So this is a hard way to compute the generators. As you can see, there are 2 different generators. One of them is 2, the other one is 3. This is how would you do this. Okay? Now, there is a better way. If you can find at least one generator, you can easily describe all other generators. Let me show you how to do this. But before doing that, are there any questions regarding this problem? Okay, let me show you how to find all generators using one specific generator. For example, here we have found the generator 2, and using 2 we can describe all other generators. Well, here Z5 star Well, we know that it's generated by the element 2. Well, what does it mean? Well, every element here is just a power of 2. And this group is isomorphic to Z4. But this isomorphism depends on the choice of the generator. And how does this isomorphism works? If you have a remainder k from 0 to 4, from 0 to 3 here, it goes to 2 to the power of k. And this is a bijection preserving the operation. So on the left-hand side, the operation is multiplication. On the right-hand side, the operation is addition. So this map is an isomorphism of this group. Because this is just the fact that 2 is a generator. So this map is a bijection, implies that this map, the fact that 2 is a generator implies that this map is a bijection. And the fact that this map preserves the operations, well, it's just a straightforward computation. Now, you see, since this map is an isomorphism, if you take an element here, let's say m, and it corresponds to the element 2 to the m, then the element m is a generator of Z4 if and only if the element 2 to the m is a generator of Z5 star. Why? Because, well, all the properties are preserved under an isomorphism. So the isomorphism says that the group on the right-hand side is exactly the same thing as the group on the left-hand side. And the element m corresponds to this element 2 to the m. So all the properties of the element m are exactly the same as the properties of the element 2 to the m. So this guy is a generator if and only if this one is a generator. So if we want to find all the generators of this group, we need to find all the generators of this group. And then map them through using this rule here, and we will get all the other generators. And for Z4, we know its elements are 0, 1, 2, and 3. And here, well, 1 is obviously a generator, 2 is obviously not, and 3 is obviously a generator because 3 is exactly the same as -1. So 1 and -1 generates Z4. So I mean, what I'm saying that in the additive case, it's easy to describe all generators. I'll tell you how to describe all the generators, but here I just want to compute them directly without any math, any advanced tools. I don't want to use tools here, just want to show you the generators. And now if you apply this map to the elements 1 and 3, you will get that 1 goes to 2 to the 1, which is 2, and 3 goes to 2 to the 3, and we have already computed that 2 to the power of 3 is 3, and this is our second generator, 3. So this is how you may compute all the generators of this group if you know this isomorphism. And what does it mean to know this isomorphism? If you have at least one generator. So now the problem is reduced to the problem of computing generators for Zn with addition. And I want to solve this in general case. So, but before doing that, are there any questions regarding this? Who thinks that he understands what is going on here?
I think I understand.
All is clear.
Okay, you may write plus in the chat, so it will be easier to follow how many people think that they can follow. Okay, good, thanks. Now I see. So as usual, if you have any troubles or you have a negative answer to my question, just press minus in the chat and I will try to explain to you. So now the question is how to describe all the generators of this group. How to find them here. So here is the answer to this question. So an element A from Zn is a generator if and only if A and N are coprime. So we may compute the amount of the generators here. So let me show you why this is true. Well, first of all, from left to right, assume that the contrary holds, that A and N are not coprime. Then there is a prime number, a common prime divisor of A and N. But then let's consider the cyclic subgroup generated by A. It consists of what? Not that. I'm sorry. Let's consider the cyclic subgroup generated by the element P, which is what? 0, P, 2P, etc. N over P minus 1 times P. As you can see, if P divides N, then this is a subgroup strictly smaller than the whole group inside Zn. Well, on the previous seminar, I described all the subgroups of Zn. So if we have a divisor of N, then each divisor of N gives you a subgroup by this rule. And here we can see that this is a strict subgroup. So there are less elements than in the whole group. So, but because of this condition, A is an element of this subgroup. So if we generate a subgroup, the cyclic subgroup by the element A, this cyclic subgroup must be inside this guy. And this is strictly smaller than the N. So A is not a generator. So a contradiction. So this contradicts to the assumption that A was a generator. And where was the contradiction? Where did it come from? It came from this assumption. We assume that A and N are not coprime. Okay, are there any?
The last line, please.
Could you repeat again?
The last line, please. Could you repeat it?
Okay. You see, if an element A belongs to a group, subgroup, this is a subgroup, then all powers of the element A also belongs to the subgroup, because subgroup is closed under multiplication and taking inverses. But the cyclic subgroup of A consists of all powers of A. So the whole cyclic subgroup of A belongs to this subgroup generated by P.
Okay, and why group generated by P isn't Zn?
Why the group generated by P is not Zn? Okay, it was already here. I was trying to explain it here. So let me repeat. So if P is a prime divisor of N, just consider the cyclic subgroup of P. Well, just by definition, how do you generate it? You take 0, P, 2P, 3P, and so on and so on. When the last integer of this form less than N is of this form, and then when you add P again, you will get 0. And then when you add P again, you will get P. So just a straightforward computation shows that these are all possible elements inside this subgroup.
Okay.
So all the elements divisible by P. So you have like P times less elements.
So I don't really understand why the last element is this.
Okay. Let's do it like this. Let's take N to be 6 and P to be 2. So you have 1, 0, 1, 2, 3, 4, 5. These are all elements from Z6. Okay. Now you take P to be 2. Then this is 1 times P. Then you add P again, you will get 4. This is 2 times P. Then you add P again, you will get 0, which is 3 times P. And then when you add P again, you will get exactly the same thing as 2. and this 2 here is n over p minus 1. Because, well, because the first time you will get 0 is, well, n over p is 3. So if you multiply 2 by 3, you will get the first, this will be the first time when the product of an integer and p is divisible by 6.
Okay, I see.
Okay, I thought I was too confusing, and I decided to like re-explain everything from the scratch. But since it's okay, then it's right. Then all right.
Wait, but then I don't understand. So A belongs to the generator to this thing. Okay, makes sense.
So it's a subgroup. So it's a subset which is strictly smaller than the whole group.
But why is it strictly smaller?
But because these are all the elements here. For example, you don't have the element 1 here. You see, there go like this. So consider this subset. It's a subgroup.
Well, okay, P isn't 1, so it's okay.
Yeah, because P is a prime number. I have taken a prime divisor. And there is a prime divisor because the GCD is not 1.
Wait, why can't we generate Zn from some P? Like,
okay, because every number that you generate is divisible by P. And since n, well, okay, let me try it again. So suppose you have your group Zn. And P is a divisor, like not necessarily P, just A is any divisor of n. You can, what does it mean? You can write all the elements in blocks. Like this. Each block has length A. And let's say something like K plus 1, A minus 1. Okay?
yeah.
Now, if you now let's generate a group by an element A. Well, if you, yeah, and by the way, what is n here? N here is k plus 1 times A. Well, because you see it's the next number after this one. This one is k plus 1 A minus 1, so n is 1 more. So now, how do you generate a group? Let's consider all possible positive powers. Well, A, the first power is A, the next power is 2A, and so on and so on. The kth power will be Ka. Now, if you take k plus 1 power, it will be k plus 1A, which is n, which is 0. So the nth plus 1 power will give you 0. So the k plus 2 power will be again A. And then if you multiply by A, you will go in circle.
Yeah, I see. So whenever A isn't 1, it can't generate the entire thing. Okay.
No. Well, here, this holds only if A divides N. If A and N are co-prime, it generates the entire group. But I mean, here there was assumption that,
I see.
Yeah, under this assumption, yeah, that happens exactly when A is 1. Yeah. So now, okay, but just in case, so there was a proof in one direction, and it was ended here. So are there any questions regarding this proof? Should I explain?
Like, so maybe I just don't. Okay, so why is A not a generator? Wait, a generator? Oh, okay, yeah, never mind. I see now.
Okay, yeah, it's not a generator because it doesn't generate the whole group. It generates something smaller, which is inside this subgroup. Okay, so now let's do it in the opposite way.
Could you please write that P isn't 1? Just write it.
Oh, okay. Let's do this. So P is prime, so it's not 1. So when I write P, I assume that P is a prime number, so I automatically assume that P is not 1.
Okay, thank you.
Yeah, I know that it's not very good to somehow assume something without explanation, but I hope it's not a huge problem. So now I want to show in the opposite direction that if A and N are coprime, then A is a generator of Zn. So how do you prove this? Well, for that, it is enough to show that 1 belongs to this cyclic subgroup. This is enough. So if we can show that 1 belongs to the cyclic subgroup, then the cyclic subgroup of 1 belongs to, so because from this it follows that the cyclic subgroup of 1 belongs to this guy. But the cyclic subgroup of 1 is Zn. It's obvious, so it will prove the required conclusion that Zn is generated by A. So every element from Zn is a power of A. So it is enough to prove this.
But probably, like, the group generated by A will be bigger than group Zn.
It cannot be bigger because element A is inside this group.
Okay.
Each power of this element is inside this group. So everything happens inside the group. So you cannot generate anything outside of the group because the group, well, everything happens inside the group.
Okay, thank you.
Mm-hmm. So now, how do you prove this? But here you use this fact, and the fact that then you can find elements U and V such that this happens. And because of this, U times A equals 1 modular N. And this simply means that the element 1 is the uth power of A. So this simply means that 1 belongs to the cyclic subgroup generated by A, because 1 is the uth power of A in an additive notation. And that's it. Are there any questions? Who thinks that he understands what's the proof?
Actually, I have a question about like the very last part. So how did we get to the conclusion? So.
Okay. So again, so what is this? This thing consists of all powers of the element A, where N is integer. Well, I'm writing like this, assuming that when N is positive, this is just a sum of N copies of A. When N is negative, this is a sum of N copies of minus A, and when N is equal to 0, then it's just the 0 element. So this is by definition the cyclic subgroup. You just take all powers with respect to addition. But what is A plus A plus A? N times, it's just N times A. So this is nth power. So since we have this equality, what does it mean? You take the element A, you raise it to the power of U, and you will get the element 1. So the element 1 is the power of the element A. So it belongs to, so 1 is represented in this form.
Oh, okay, but the question is about, so how do we go from UA plus V N equals 1 to?
Oh, you take this equality modular, N. Then it goes to 0.
Okay.
Okay, so that was the question. I didn't recognize that that was the place. Okay, are there any other questions?
Could you clarify again why one is within a group generated by A?
Why one is here?
Yes.
Okay, so this is just the another way of so this is just a reformulation of what is underlined by the red here. So what's written here? Well, what we have here is just 1 is equal to A plus A plus A U times. And this is just by definition means that 1 belongs to this group.
Why?
Because by definition,
okay, yeah, I see.
What is this group? You just take A and you add it U times, where U, well, if U is positive, then this is precisely this expression. If U is negative, then you just add -1 plus minus A plus minus A plus minus A module U times.
But U times A is equal to 1 by modulo N. I mean, A U times isn't 1, it's 1 modulo N. It's like, it's different things.
Again?
You
repeat.
You wrote down that U by A is 1 modulo N. And after that, you write that A plus A U times is 1.
Well, but yeah, but it's I mean it happens in Zn, so it's modular n.
Okay, yeah.
So it's also modular n. I mean, I think of this as equality in the group Zn. So I'm just interpreting this equality in a specific way. So here it's written explicitly that equality modular n, but here, since this happens in Zn, the equality modular n just by definition is just assumed implicitly.
Okay, thank you. But doesn't imply that every element is 1.
Why?
Because we have shown that how to say?
We started from this condition. You see, if A and N are coprime, then 1 is a power of the element A. That's what we have proved.
Yeah, but we know that A and N, they are coprime, so we can write that UA plus Vn equals 1.
Okay.
So it implies that every element UA is 1 modulo N. So within group generated.
Here there exists U and V such that this equality holds.
Okay.
Yeah.
Thank you.
So this is the extended Euclidean algorithm. It says that there exists U and V such that this property holds. Are there any other questions? Okay, so let me summarize what happens here. So an element A from Zn is a generator if and only if A and N are coprime. So now let me apply these. Okay, let's solve another problem. Let's compute the generators for Z17 star. 17 is a prime number. So Z17 star is a cyclic group. How many elements are there?
16.
Again?
16.
Yeah, 16. So this must be isomorphic to Z16. Okay? So let's compute how many generators are there in Z16. So how many generators here?
At least 2.
Okay, so what are the generators? An element here is a generator if and only if A and 16 are coprime. But since 16 is a power of 2, this is equivalent to saying that A and 2 are coprime. But this is exactly the same as saying that A is odd. So how many odd numbers from 0 to 15? 8. So there are 8 generators here. Who with me? Who thinks that he understands? Okay, cool.
And we used our previous property, right?
Yeah,
That,
yeah.
Okay.
So this simply means that this group has 8 generators because of this isomorphism, because there are as many generators on the left hand side as we have on the right hand side, because the groups are isomorphic. So they are basically, this is basically the same group, but it's represented in a different form. So this is the power of isomorphism. If you find an isomorphism between your group and some other group, and the other group is easier to understand, then you can get all the properties from that other group to understand your initial one. Okay, so now we know how many generators we have. You see, the half of the elements, they are generators. So if you just randomly choose one after another one with probability 1/2, you will get the generator. So let's try this approach here. So let's name all the elements of Z17 star. They are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So these are all elements of the 17 star. Now, well, we know that one cannot be a generator, so it's simple. So let's try 2. Let's find the order of the element 2. If the order of the element 2 is 16, then this is a generator. So when we 2 to the power of 2 will be 4. Rising again will be 8. Rising it again will get 16. So it's easy because here all the numbers are smaller than 17 and we didn't reduce modular 17. But now we may use a trick. Instead of multiplying 2 by 16, we use the fact that 16 is equal to -1 modular 17. So this is exactly the same thing as to compute 2 times -1 modular 17, and this will be -2 modular 17. But modular 17, this is what? 15. So the next power is this, 15. Now, if we multiply this by 2, again, we will get -4, and -4 modular 17 is 13. Now, if we multiply -4 by 2, we will get -8, and -8 modular 17 is 9. So we'll get -8. And now if we multiply -8 by 2, we will get -16, and -16 is -1 times -1. It will give you 1, the neutral element. So as we can see, so 1, 2, 3, 4, 5, 6, 7, 8. So the order of the element 2 is 8. It's strictly smaller than the required order. So 2 is not a generator. And all powers of the element 2, which are the blue numbers here, they are not generators. So is there any question regarding what was here?
Wait, but didn't we just prove that like a number is a generator if and only if it's co-prime with the size of the...
But that was for Zn without star. Here,
Oh, okay, sorry.
Zn star is much harder to understand than Zn. And this is the problem.
I didn't notice for some reason, sorry.
No problem, no problem. It's okay, since you see the difference between you and me, I know all these objects for a very long time. So I know all the subtleties. I know where to find, where to look at. And there are a lot of information. There is a lot of going on here. And it's really hard to remember everything, and it's really easy to miss something and misinterpret it or misunderstand something. So it's okay. So that's why you should ask questions. So now let's count how many n elements are left. Exactly 8 elements. So we know that all the blue elements, also we need to underline this one, all the blue elements are not generators. And there are 8 generators. There must be 8 elements which are generators. And we found 8 elements which are not generators, and there are 8 elements left. So all the red elements are generators automatically. So we don't need to compute the orders of all other elements because of these fact that we know how many generators there must be. We know that all the other elements are generators. So 3, 5, 6, 7, 10, 11, 12, and 14, they are generators.
But how do we know how many generators there should be?
Okay, that was the first step here. We know that this group must be cyclic. It's Z16. And for Z16, we know that there must be 8 generators. Here we have computed the number of generators using the previous claim. Okay. So this is how you may simplify your computation using several facts. So this is not a silver bullet solution. So, I mean, it's just some trick to simplify your computation in a situation when it works. When it doesn't help you. So, but it may help you. So it's a very useful trick. So just keep in mind that you may, well, if you have chosen an element, like here we choose 2, and it doesn't work. It doesn't give us a generator, but it gives us the set of elements which are not generators. And if we know that how many generators we have, and we can always compute how many generators we have, then we may automatically get that all the other elements are generators. So we don't need to go through all this computation, for example, for the element 3, 5, etc., and so on. So this is how we do this. So at the end, we have this isomorphism that the Z17 star is isomorphic to Z16 by the rule k goes to 2 to the k, or 3 to the k, for example. And we may use any generator here. So we may use 5, 6, 7, 10, 11, 12, or 14, any. So so different generators give you different isomorphisms. So for each generator, you have a specific isomorphism. Well, as we discussed, a homomorphism from this group to another group is given by the choice of the image of 1. Okay. Now I want to discuss a similar problem, how to check that an element is a generator in a group of a specific order. So let's try this. So suppose you have a group G, which is a finite group, and we're given an element G from the group G. And the order of the group is n. So the claim is this. So, and let's say that n is a product of primes of this form, p1 to the k1, etc., pr to the kr. And p1, pr are all distinct prime numbers in a factorization of n. So the claim is this. So G is a generator of G capital if and only if G to the power n over pi is not a neutral element for all I. So this is the way people check if an element is a generator. You don't actually need to compute all the possible powers. You may simplify the computation in this way. For example, so let me show you how this helps, for example, in the previous case. So when we have the group Z17 star, this is our group G. Its order is 16, so it's 2 to the power of 4. So we need to check for an element that 16 over 2, so G to the power of 16 over 2, which is G to the 8, is not 1. So an element is a generator if and only if its 8th power is not 1. So this is how to apply this criterion to the previous case. And as we can see during the previous computation, we have checked that 2 to the power of 8 is 1, so it's not a generator. So it's not a generator. But if we compute 3 to the power of 8, we can do it using the fast algorithm. So what is this? It's 9 to the power of 4. Then, well, we need some computation. There must be some work to do. It's easier to do by computer, but okay. So 9 by 9 is 81 to the power of 2. Now we may reduce 81 by 17 and then just complete the computation, and we will see that this is not 1. I just don't want to waste my time because I didn't pre-compute all the numbers here. So this will show you that this is a generator. So this is just an example of the previous claim. So if you want to check that something is a generator, it's enough to check these properties. So are there any questions regarding the claim itself, what it means and how to apply? Okay.
Can you repeat it?
Okay. If we have a finite group and the order of the group is n, and we can factorize n as the product of primes as it's written here, then an element of the group G is a generator if and only if G to the power of n over pi is not the neutral element for all prime numbers pi from p1 to pr. So you don't need to check all the possible powers. So this is what is essential here. Okay.
Yep.
Yeah, and how to prove this? Well, it's actually a straightforward thing. Well, it's similar to what we did for the cyclic group. So, okay, let's do it. Well, first of all, from left to right, it's easy. So if G is a generator, then we know that the order of G is the order of the group, which is n. So n is the smallest possible integer such that G to this power is equal to 1. So G, if we divide n by any prime divisor, it will be strictly smaller integer. So it must be it cannot be a neutral element, the neutral element. So from the left to right, it's simple. So we should go from right to left. And here we must assume, let's assume that the contrary holds, that it's not a generator. If it's not a generator, then its cyclic subgroup is strictly smaller subgroup than G. But if it's strictly smaller subgroup, well, you see, this integer is of this form. And if it's strictly smaller, then it means that some prime number here is missing. So the order of this group must divide n over pi for some pi. Well, I mean, there could be several prime integers missing, but at least one is missing. So the order of this subgroup divides n over pi. And by one of the corollaries of the Lagrange theorem, this means that this is true, and this contradicts to the condition on the right. And the contradiction appeared because we assumed that G was not a generator of the group G. So this is how we prove it. Okay, so now I want to discuss another question. Well, before doing some cryptography, yeah, and I have like 30 minutes. Okay, yeah, we have enough. So we discussed how to compute a generator of this group, ZP star. Well, we did it for several examples, but let's discuss how to compute a generator for a group of this form. Let me recall the claim how to check if something is a generator for such a group. There was a claim saying that an element A from ZP to the K star is a generator if and only if the following two conditions hold. A modular P must be a generator of ZP star, where K is 1. And the next one says that A to the P minus 1 is not equal to 1 modular P squared. Well, this is somehow, well, I didn't explain you why this is true, but well, as you may guess, this is true. So let's try to use this tool as a black box. But this works in well, this works in case of odd prime number. So let me be more specific. So this is for odd prime numbers. There are not so many even prime numbers, but the even prime number is the most disgusting one. So there are a lot of exceptions when P is even prime. But for odd prime numbers, there is the way to check if something is a generator. So let's try doing this for the group Z, well, 125 star. So what is this? This is Z5 cube star. So first of all, when we apply this result, we need to find all the generators of ZP star. So here it's Z5 star, and we already know all the generators here. All the generators here are just 2 and 3. So the first condition translates into the following one: A modular 5 is either 2 or 3. So this is the first condition. for the remainder of this group. And the second condition says that A modular what? 5 minus 1 must be not equal to 1 modular 25. So now we just need to go through all the numbers of this form and find the generators. Let's do this. But before doing that, who is following me? I mean, how many of you can follow me now? Okay. Are there any questions? Okay. So the condition number 1 suggests that we have two cases. The case number 1, A is equal to plus 5k. The case number 2 says that A is equal to 3 plus 5k. And now we want to check that A to the power of 4 is not equal to 1 modular 25. So we want to check this condition. Well, actually, this is done by a straightforward computation. So how many k numbers k we need to check here? Well, you see, since these guys live in Z5 cubed star, then, well, if you multiply 5 by 25, you will get 0. So you check all the numbers k from 0 to 24. So we have like 25 cases. And for all 25 cases, we compute the fourth power of this element and check if it's 1 or not modular 25. And this will separate good and bad cases. So if we have equality, then it's not a generator. And if a to the 4 is not equal to 1, then this is a generator. Is not a generator. Well, I believe it's a bad idea to do this computation right now, but this is how you do this. You just go through all the options and check, well, if it's 1 or not. But if you want, I can do one case. For example, if k is equal, let's do it like that. If k is equal to 0, then a is 2, and you just compute 2 to the power of 4, which is 16, and you take it modular 25, and modular 25, it's not 1, so 2 is a generator. And then you just add 5, which is 7, and you compute 7 to the power of 4. You take it modular 25, and if it's not 1, then it's generator, and so on and so on and so on. So this is how you do that. Okay.
Should we do the same for A equals 5k plus 3?
Yeah, and you do exactly the same for the second case. So there is a lot of computation here. So that probably was not a good idea to take the third power. It would be better to take the second power for an example here for the next time. Okay, that was a bad choice for me. I'm just randomly inventing numbers here. So yeah, it's an unpleasant task, but well, it's doable. But what is important is just to understand how this mechanism works. So you just check all these things. Okay, so let's try doing something more interesting. Let's go and do some encryption and decryption. So let's try this. So I want to, so cryptography. So I want to choose, I want to choose some specific group. Let's take G to be Z5 star, a small group. Well, in practice, you should take a prime number here, very huge. But if we take a huge number, we won't be able to compute anything. So let's take Z5 star. And we already know that it consists of these elements, and 2 and 3 are generators. And let's take G, the generator, to be 2. So this fixes an isomorphism of this group with Z4, like this. Okay. And the order of the generator here is 4. So this is the data we use to encrypt and decrypt information. So what is information in our case? Let's say that the information, a message, will be a string of zeros and ones, something like this. So this is a message. So in order to apply any encryption and decryption, we need to translate this message to the elements of group, to the sequence of elements of group, of the group G. How do we do this? Well, we need to fix some translation. For example, when we choose this form of translation, let's divide this sequence into pieces with 2 symbols, and then we map 0, 0 to 1, 0, 1 to the element 2, 1, 0 to the element 3, and 1, 1 to the element 4. And now we have a bijection between all the strings of 0 and 1 of length 2 and the elements of the group G. So here we have strings, and here we have Z5 star. And here is a bijection. Well, in general, it's hard to produce a bijection between our initial messages and the group. And in general, we just find an inclusion. So we want to include all possible sequences to our group. And we want to find, we want the amount of elements here to be as close to the amount of strings here as possible. But here we have a good situation where we have a bijection. So now if we want to translate this sequence, how do we translate this sequence? Well, we do this. 0, 0, 1 is 2, then 1, 0 is 3, then 1, 0 is 3, 1, 0 is, oh, it's not an interest. Let me replace this guy by 1, 1, because it's not interesting. Otherwise, we have a repetition here. So this is a sequence of elements of the group G, which is Z5 star. Now we may apply the process of encryption and decryption. Okay, so give me a second. Let's do this. I want to see my notes in order to compute everything faster. I just don't want to waste time for computation of everything. Okay, so here we must have 3 participants. You, suppose, my handwritings are awful, and the lover. So everyone knows that we use Z5 star. The element G is 2, and the order is 4. Now we need to find we need to generate a public key. In order to generate a public key, we need to invent an integer a from Z4 here and an integer b from Z4 here. Well, which one to take? Okay, let's try the elements 2 and 3. Let's assume that we have taken the element 2 and our lover chose the element 3. Okay, now let's generate the public key for ourselves. What should we do? We should compute g to the power of 2. This will be our public key. What is g to the power of 2? Well, g is 2, and we need to find the second power of the element 2. How do we do that? Well, 2 to the 2 is 4, so in this case, this is just 4. Now, what does our lover? Our lover must compute 2 to the power 2 to the power of 3. Well, 2 to the power of 2 is 4. 4 to the 4 times 2 is 8, and modulo 5 is 3. So the public key for our lover is 3, and we say this information to everyone. So these are our public keys. Now, let's compute the private keys. Well, the private key. So how do you compute the private key? Well, the private key must be g to the power ab. Well, since we know all the information, we see that this must be 2 to the power 2 times 3, which is 6. So we want to compute 2 to the power of 6. And this will be our private key. But let's see how we compute this private key. We take the public key of our lover, which is 3, and we raise this element to the secret number A we have chosen, which is 2. So for us, the computation of the private key is raising 3 to the power of 2. And 3 times 3 is 9, and 9 modulo 5 is 4. So this is how we compute the private key. So let's see how our lover compute the private key, and if the private key be the same. Okay, so our lover must take our public key, which is 4, and raise it to the power of 3, which is secret number he chose, or she. Then what is this? 4 times, well, here we know that 4 times 4 is 1 modulo 5. So 4 to the power of 3 is just 4. Let's write it. So this is how our lover computes the secret key. As we can see, the secret key is 4 in our case. And now we know all the secret information required to encrypt and decrypt the data. So are there any questions regarding this first stage of key exchange in this particular case? Who thinks that he understands what happens here? Okay, Nikolai, do you have any specific question?
Well, no, I just, I think I'll go through it, well, again later, because I
Okay.
don't feel that I have the whole picture in my head. Yeah.
Okay, but just in case, so as always, I use yellow color to indicate the information that everyone knows. By the red color, I indicate the information that only you and your lover know, or just you or just your lover, some secret information. And the blue information is something that you can translate through an open channel. Okay, so let's try to encrypt and decrypt the data here. So here's our sequence: 2, 3, 4, and 3. This is the sequence of messages. So now messages. So we have a sequence 2, 3, 4, 3. So how do you encrypt this information? You multiply each message, which is an element of the group Z5 star, by the private key, which is 4 in this case. So let's do this. If you multiply 2 by 4, you will get 8, and 8 modulo 5 is 3. If you multiply 3 by 4, you will get 12, and 12 modulo 5 is 2. If you multiply 4 by 4, you will get 16, and 16 modulo 5 is 1. And again, if you apply the same rule to the element 3, you will get 2. So this is the sequence of encrypted data. So now we translate this sequence to our lover, and it gets the information 3, 2, 1, 2. Now we want to decrypt the information. How do we do this? We need to take our secret key, which is 4, and we want to find key inverse. But if you, well, here, how do you compute this? You just raise key, k to the power of 4 minus 1. Why? Well, because 4 is the order of the group, k to the power of 4 is just the neutral element, so the left-hand side and the right-hand side might be the same. But now you just need to compute a positive power, which is 3. So we need to compute k to the power of 3, which is 4 to the power of 3. And as we can see here, 4 to the power of 3 is also 4. So we see that k inverse is also 4. So in order to decrypt these messages, we need to multiply by 4 again. So let's multiply each element by 4 again. So multiply by 4. So if we multiply 3 by 4, what will we get? We will get 12, and modulo 5, it will be 2. If we multiply 2 by 4, we will get 8, and modulo 5, it will be 3. If we multiply 1 by 4, it will be 4, and modulo 5, it's 4. And here we'll get, again, 3, because we already know how to apply this to element 2. And now if we compare the sequence, we will get the initial sequence. And now in order to understand the message itself, we need to apply this table for translation, which is written here. As you can see, the element 2 corresponds to the sequence 0, 1. The element 3 corresponds to the sequence 1, 0. The element 4 corresponds to the sequence 1, 1. And the element 3 again corresponds to the sequence 1, 0. And voila, we have decrypted the initial message. So let me repeat what happens here. So first of all, before doing anything, we need to choose the following data. We need to choose a group G, a cyclic group G here, its generator, and compute the order of the generator, which is the order of the group. We could take the element 3 here in this particular case, because 2 and 3 are generators. It doesn't matter which generator to take. But the next thing we need to do is to fix the table of translation, which is this. This is the way how to translate a meaningful message. Well, here message is not that meaningful. It's just a sequence of 1s and 0s. But let's assume that this is a meaningful sequence for us. And if we want to translate this meaningful sequence to an element of a group, we need to specify this translation. Well, this can be done in any way or shape or form. Like literally, there is no rules how to produce this translation. Just take any mapping you want, like literally anything. The only thing which is essential, the map from left to right, which takes strings to elements of the group, must be injective. So different strings must go to different elements. Well, this map need not be surjective, but this simply means that some elements of the group, they do not correspond to a string, to a meaningful string, and they will not appear while the decryption process. So now, when you have all this information, the group, a generator, you computed the order, and you fixed this table, now you can start the communication process. And how do you do this? You do this in 2 steps. The step number 1, you need to generate a secret key using a public channel for messages. And the second stage is sending messages. So before you can send any message, you need to generate a secret key. So you cannot start messaging before you have this secret key. And just to clarify what's going on, remember, a message here, so after you use this table, your message is an element of this group G, which is the 5 star. And encryption is multiplication by the secret key, and decryption is multiplication, is division by the secret key. So let's put it that way. So from the algebraic point of view, your operations are really simple. You just multiply by an element, and then you divide by an element. So the only tricky part is how to produce this secret element without communicating directly. For example, if I want to communicate with a bank, I don't want to go to the bank. If I want to communicate secretly with something from like North America, I don't want to buy a ticket to North America and say privately this secret key to my partner. I want a way to communicate through an open channel without worrying that someone can find the secret information. So the first stage is just a tricky way of communication, and as the result, you will produce this piece of information, the secret key, and the secret key will be known only for you and your lover. So the only goal of the first stage is to provide this secret key. There is no other goal. There is no communication here. There is no message sending here. The only reason for the first stage is to get this secret information. So this is the most important thing that happens in the first stage. And only the second stage is used to communicate. So this is how it works. Okay, guys, who thinks that he followed through the whole example from the beginning till the end? Okay, who thinks that there are some problems with this process, or I should clarify some details, or something is vague or unclear? Okay, and who thinks that he can translate a message if I tell you all the yellow data? Okay, I see. That's good. So, as I can see, I have like minus 1 minute left, and this is exactly the place where I wanted to stop. So I actually explained you everything that I wanted, and we solved almost all the problems that I wanted to solve. So there are some additional, well, as usual, there will be some additional problems for seminars. So if you want to, to solve something except the homework, like something more than just the homework, you can solve those problems that we didn't solve during the seminar. I will leave these additional problems as usual. So yeah, are there any questions regarding this seminar? Okay. If there is no questions, oh, okay.
I have a question.
Yep.
A lot of questions, actually. Yeah, but I would ask them after everyone leaves the conference. It will take a lot of time.
Wait a second. There is a question in the chat. I want to read and answer. Will the homework be until the next seminar or until third? We have. I see. So the problem is the next week is it's a holiday week. So I believe you have 2 weeks for the homework. Yeah, so I think it's fair. I mean, it doesn't make sense to restrict this till one. Well, to restrict you to make such a restriction like 1 week, because everyone will spend these holidays like doing nothing, so no one will check your solutions during this during the next week. So it doesn't matter, but it will provide you with more time to think about the problem. And I believe the cryptography is probably one of the most important part of this course. So if you can understand how it works, it would be better. Okay. Are there any other questions? Okay, Kirill, I believe now it's your time to shine up.
Okay. First question about the first claim from the lecture. I didn't get how did we prove that it is bijection?
Okay, so